How do you find a place on the earth? I wanted to tell somebody to come here to Seton Hill. And they knew nothing about the roads, maps, any of it. How would we find this place on the globe? Longitude and latitude, wait a minute. I'm describing the surface of a sphere, but I only used two coordinates, just like X and Y. Longitude and latitude are a pair of parameters that I can use to describe a surface. Oh, okay. I'm not sure I want to use longitude and latitude, particularly because latitude doesn't really obey the coordinate system rules I like in the same way, because it's not relative to like the origin, like our spherical coordinates. Maybe I could use the angles, like just theta and phi, because then I would be able to say we have a uniquely defined prime axis, the prime meridian, and I can measure my longitude, and then I can measure it from the pole down. That would be my phi angle, the way I described it in spherical coordinates. But I can take what was a curve I can do this in 3D, I can do it in 2D. I'm going to think about it in 3D for the moment, but a curve in 3D, if I change that from one parameter to two, that's a surface. That's a parametric surface. But what does that mean? Well, that means that R of UV has to be 3 two-variable functions. If I think about longitude and latitude, I know the radius of the Earth. All I have to tell you is what longitude you're at, what latitude you're at, you know exactly where this place is. I could define the entire surface of the Earth by saying a point on the surface, X, Y, Z, is defined by its longitude and its latitude. Those are the U and the V that go with it. All right, but if this means that U and V have ranges. This is a very different definition of how we defined a function from thinking of the function as a graph. But there's a parallel here. We're going to think of the surface S over the domain D. So in longitude and latitudes, the numbers go from 0 to 359.999 and from 0 to 180. Well, 0 to 90 in two directions, right? Northern and southern hemisphere if you count it separately. Positive 90 and negative 90. Okay. But with that range, I can then describe something. Let me think about this a little differently. Here is a two-parameter vector function. Instead of writing it as I, J, and K, I've written it in its component form, but that's still the same idea. 2 cosine of U times I, V, and then 2 sine of U. And now I'm going to make our domain D. I'm going to say, 0 less than or equal to U less than or equal to 2 pi, negative 5 less than or equal to V less than or equal to 5. My stupid question of the day. This describes a surface, an object in 3D. What's it look like? I can tell right away, whatever it is, the y values only go from -5 to 5. So it's a chunk from -5 on the left to 5 on the right. And the only y value, the only way y, the only thing v affects is that y direction. So let's look at x and z. How do x and z relate to each other? Or to this expression here for the domain for u? Hang on a second. If I ignore v, what's that a parametric description of? Say again? A circle. A circle of radius 2 centered at the origin. Oh, so it's a circle in x and z, right? So it's a sideways circle. Along the xz axis, I have a circle. And as a matter of fact, this is a circle of radius 4. Sorry, of radius 2, because it's x squared plus z squared equals 4. Wait a second. In x and z, it's a circle, but y is free. The only thing I know about y is it goes from -5 to 5. It doesn't have any effect on x, doesn't have any effect on z. Sorry, the parameter v doesn't have any effect on x, doesn't have any effect on z. What's this shape look like? Cylinder. It's a finite piece of a cylinder. Please excuse my horrible artistic merit. Wait a second. If we fix the value of u, then we fix x and z, right? As v changes, what happens for a fixed u? Oh, no, this is x, y, and z. Oh, well, these are the axes, x, y, and z. I'm drawing the curves we've created. If I fix u, then x and z are fixed. What happens as v changes? I move along the cylinder from left to right, yes? If I fix v, then I fix a y value. What happens as u changes? I'll go around the circle. So I can think of covering this surface in a grid created by drawing the lines in u and the lines in v. If I fix a value of u, let v change, I'm going to get stripes going left to right. If I fix v and I let u change, I'm going to get circles going around this. When we graph stuff in the grapher on our MacBooks, it almost always defaults to a checkerboard pattern. So what I'm going to do is I'm going to draw on this set of 3D axes exactly the equations we just created. Our equations are in X and Y and Z as parametric. So I'm going to make a 3D parametric curve. But instead of writing that as a curve and just putting in T, I'm going to put in U and V. So up here, 2 cosine of U, then V, then 2 sine of U, and then I tell it U goes from 0 to 2 pi, comma, V goes from -5 to 5. So I can give it the ranges just like we did for T back when we were doing parametric curves. I can give it the ranges for U and V. There's my cylinder, and it even drew the freaking checkerboard on it, didn't it? And you can see, if you hold a value of V constant, you fixed a Y value. There's the x-axis, there's the y-axis. So if you fix a y value, you're going around one of these rings. If you fix a v, then you go around one of these rings. If you fix a u, you fixed a point on the ring and you go along one of the lines. We call these the rulings of our curve, like we took a piece of graph paper, lifted the lines off of it, and put those on our surface. Now, wait a second. That's the equation for our cylinder in 3D back in chapter 12, right? When we did cylinders, cylinder chapter 12, section 6, cylinders and quadric surfaces and all that fun crap. We did this. Which means I can think of graphs of functions this way if I can figure out what to write. Some of these are nicer than others. Okay, I'll mess with your heads now. U cosine of V U sine of V U squared. This time, U is going to go, say, -3 to 3, and V is going to go 0 to 2 pi, because that's the one for the trig functions. Sine and cosine, right? I'll use 0 to 2 pi. As soon as I hit enter, it's going to draw the picture. The hell is this thing? Even before I do anything else, what does this look like? Let's pick a variable to fix. You want to fix U, you want to fix V. If I fix U, then I could think of that, let's pick a number. How about 1, right? Then I would have 1 cosine V, 1 sine V, and 1. What does that draw? X equals cosine, Y equals sine, Z equals 1. What does that draw? Draws a circle at a height of 1 and a radius 1. Pick another value for U. Say again? 4. Then I'll get 4 cosine U, 4 sine U, and 16. Wait a minute. I'm drawing a circle of radius 4, but now it's the height of 16. So if I think of cuts parallel to Z, because Z gets fixed when I fix U, I get circles. So I'm getting a stack of circles somehow. Let's fix V. If I fix V, V says cosine V sine V, right? Cosine V sine V, that gives me a point on the unit circle. That's a direction. So if I fix U and V, I'm sorry, if I fix V, it's saying in X and Y, go a particular direction. How far? That depends on U, the value of U. As U changes, we get X equals U times some number, V, or Y equals U times some number, but Z equals U squared. We're going in a particular direction. As we go, we're drawing what shape? Drawing a parabola. This should be a paraboloid with circles as cross section. And there are the circles going around, and there are the lines for fixed values of V, different angles going around. Now, I will say that one of the better things about this graphing program and this idea in general is that I can see these grid lines. I can see what happens when I fix things. Sometimes parentheses, 2 plus sine of V times cosine of U, 2 plus sine V times sine of U, and then U plus cosine V. Oop, don't delete the whole damn thing. That would piss me off. U plus cosine V. Now, since both of my arguments are in trig functions here, I'm going to let both of these go from 0 to 2 pi. What the hell is this? Again, I haven't even hit go yet. Let me think about this. You want to fix U or do you want to fix V? Okay, if I fix U, then cosine of U and sine of U are constants. And this U is a constant right here, yes? So I get 2 plus sine V for X and Y. Wait a minute, X and Y are the same. But as sine goes from 0 to 2 pi, but Z is going to go cosine, right? So I get 2 plus sine, and cosine. I get a circle, but its center is moved. On the other hand, if I fix V, I get number times cosine, number times sine. That's changing my radius. That's a circle, cosine and sine. And then U changes, which means Z goes up. Wait a minute. I'm going in circles as I'm going up. What am I drawing? I'm drawing a helix. But I'm also, at every point on that helix, drawing another circle. What I actually get is a 2 in a helix. That's a really complicated surface, isn't it? By the way, it's called a helicoid. They call it a piece of funny looking pasta. Right? Okay. But now I can say, oh, if I fix U, I'm going up the spiral. If I fix V, I'm going up the spiral. If I fix U, I'm going around the cross-section circle. There's the grid exactly the same way. Why? Promise there's a reason for doing this. I want to be able to switch back and forth between graphs we already know and other surfaces. So let me think about the sphere, right? We had a sphere. And I could ask you, hey, what's a set of parameters I can use to describe this surface? We came up with latitude and longitude. But I also think we could use our spherical coordinates, right? And if I use spherical coordinates and I have x equals a, now I have to remember what it is. It's a sine phi cosine theta. Y equals a sine phi sine theta. And z equals a cosine phi. And again, I would say phi goes from 0 to pi, and theta goes from 0 to 2 pi. And that uniquely describes a point anywhere on the globe of radius a on the surface. And now I have a two-dimensional idea for describing this three-dimensional object. A short diversion into mathematical terminology. A surface is one dimension smaller than the space it lives in. Think about this. The surface of the table, two-dimensional, in a three-dimensional world. The surface of my body is a two-dimensional surface in a three-dimensional world. What I'm doing is I'm describing the surfaces as smaller than the spaces they live in. So we would call something that has two parameters a two-dimensional manifold, because it's a two-dimensional surface. Whether I put it in three-dimensional space or 17-dimensional space doesn't matter. It's a two-dimensional object. A parametric curve is a one-dimensional idea because it's only got one parameter. So where we think of dimensions as the way we measure where we are things in space, they can actually be thought of as characteristics of the object themselves. So what I'm trying to describe here is the way in which we look at manifolds in two dimensions. Now I know this is a stretch, but based on chapter 12, section 6, and your note card for the first exam, do you know what that surface is? It would only be a cone if it was equal to 0, because what I need is one square on one side and two squares on the other side to get a cone. A hyperboloid of one sheet. So this equation, x squared is positive, y squared is positive, one of them is negative, equals 1. That's a hyperboloid, and it's one piece. If two of them are negative and one is positive, then I get the hyperboloid that's two pieces. So this is a hyperboloid of one sheet, but I only want part of it. I only want where y is positive. So I only want the right half. Or left half. Depends on which way I'm looking at. I only want one half of this. I don't have a parametric set of equations for here, do I? But That's still a surface. The surface of that hyperboloid of one sheet is itself a two-dimensional manifold. I should be able to write it in terms of two letters. But of course, if I know y is bigger than or equal to 0, I can take this equation and solve for y. And since I know I want y to be positive, I can use positive square root. And now this surface is defined in terms of the two variables x and z. So I could think of this as a set of parametric equations. Where x and z are the parameters themselves. Instead of using u and v and other letters, I can use the equation itself, which means any surface that is a graph hey, this is the one we did for all of chapter 14, z equals f of x, y. I can say a parametric set of equations comes from using this, and then y equals y, z equals z. Using this, x equals x, z equals z. Using this, where x and y are the parameters themselves. Describing anything we have a graph of is automatically a two-manifold if I've written it as a function. Where I'm going to use the R version, the R of u and v, is when my equation can't be drawn as a function. And if you think about that weird-ass looking piece of pasta, that doesn't pass the vertical line test, does it? It fails to be a function of x and y. Then z is going to hit it more than one place, isn't it? I can't write that as a function, but I can still describe the surface, the whole surface. I can't write a sphere as a function of x and y, but I can write it as a function of theta and phi. I can use functions instead, as long as I rearrange them to be parametric. Why? Why on God's green earth do I want to do this? Well, it turns out that when I am working in functions, my life gets a lot easier. When I had to go through and say, well, if we're on the top half of the sphere, we're going to use this equation. If we're on the bottom half of the sphere, we're going to use this equation. It always got weird at the edges, right? It didn't draw the edges of my circle properly. Now I can say, screw that. And if I use theta and phi as my parameters, I can draw a sphere immediately of any side, and it'll graph perfectly. It's not two equations anymore, it's just one. And we started playing with equations, and we really didn't think about the way we did them. I'm going to jump back to Calc 2. We did, yeah. We did surfaces. We did back in Calc 1, we did volumes of revolution, right? You took a curve, you rotated it around the x-axis, we found the volume. And then in chapter 8, we took that same curve, rotated around the x-axis, and found the surface area. And finding the surface area was a pain in the ass, because we needed a way to figure out my derivatives. We did this again in chapter 14, right? We had the partial derivative thing, square root of 1 plus partial with respect to x, partial with respect to... We did this. We found surface areas. But let me think about this again. I have some curve f of x. I'm going to rotate this curve around the x-axis. What I'm creating is a two-manifold, a two-dimensional manifold. I've built a surface, this piece of a tube, right? If I want this tube this surface. What's the equation for this surface? Wait a minute. If I'm at some x value, what's that point? That's the y value associated with that, right? That's f of x. But then I'm taking that point and I'm moving it in a circle. And I'm changing the y value and the z value, but I'm not changing the x value. As I go this way, the y value changes. From this perspective, if that's x and that's y, z is sticking out at us. Take your hand, x and y in front of you, right? Now point your first finger up, you're looking at x and y, and then your thumb is sticking right into your face, isn't it? So the z-axis in this picture is here. Technically, I need to rotate my hand so my forefinger points over to the right. That points along the x-axis. Yes? X, Y, Z. I can cheat and tell you this is F, I, and B, right? That's the electricity and magnetism people over in the physics class. So there's my z-axis. But that means that y and z are going to change. They're going to move in a circle. So what I can do is I can say, oh, y is going to be the radius of my circle times cosine of theta. And z is going to be the radius of my circle times the sine of theta. Oh, and x doesn't do anything. It just tells me what the radius is at that point. Notice that the surface is now a two-parameter family. It is a function of two variables. It is the function of x and theta. So I can write r of x theta. And now I have a description for this surface in two variables. Any surface I can make, I can turn from some graphing expression to a function of two variables. Even if I leave some of those variables alone. I got a question for you. I got a function of two variables. I get to take derivatives now. That function, x and theta, has a derivative with respect to x. It has a derivative with respect to theta. Let me go back into a simpler version. We'll use this one. We'll use our cylinder, because that one's easy to picture. Here's my cylinder. Let's roll up my piece of paper. So let me write that equation down again. I have R. This is what happens when I don't write for a day as my pen jams. Let's try again. I have R of UV equals 2 cosine U V 2 sine U. All right, I would like you to take derivatives for me. I'm back in Calc 1. I'm back in Chapter 14. What is R with respect to U? What is R with respect to V? While you do that, I'm going to go draw the cylinder back in the graph. Put in the wrong variable at first. What are my partial derivatives? What's RU? And RV? Oh, that's nice and easy. So let me ask you a question. What direction does RV point on my cylinder? Points in the positive y direction, yes? 0, 1. Wait a minute. That's along those lines, isn't it? Ooh, that's a tangent vector. It's going along the surface in this direction. Not only that, it's a unit tangent vector because it's 1 unit long. It's a tangent vector. All right, wait a minute. Here's the x and z variables, right? I turned it so y is pointing away from me, so I'm looking at x and z. As u gets bigger, which way are we going around this circle? Are we going clockwise or counterclockwise? Help if we look down it. That's x, that's z. No, I think it's better with x on the right. Are we going clockwise or counterclockwise? Which way are we going around this circle? Is x gets bigger, as u gets bigger, x gets bigger. As u gets bigger, z gets bigger, doesn't it? So as we start over here, we go up. We're going this way. So from this perspective, we're going counterclockwise. From this perspective, we're going up. From the x-axis, we're going around the circle, x and z. You're looking at me like I'm a space alien. Let me draw you the picture the other way. Here's x and z, just x and z. This equation, when u is 0, starts here at a radius of 2 and goes this way. Right? So remember, that's x and z. So back over on our cylinder, here's x. We're going this way around the circle. Now, think about our tangent vector, -2 sine u cosine, comma 0, comma 2 cosine u. What about this vector? Where is it on here? It's a tangent vector. And that means it's pointing this way as we go around the circle, isn't it? My one vector points, RV points along this curve. RU points along this curve, along the circle we're traversing. These make tangent lines on our grid. So if we were looking at one of those really fugly looking surfaces, there's our funky looking pasta. R of U would be going around this circle. Sorry, that's where U is held constant. That's RV. Where V is held constant, we would be going up the spiral. We'd have a little vector going in each of those directions at every point, wouldn't we? Wait a minute. If I have a little vector at each of those points, look at this little grid thing. What shape is that little grid thing right there? That little piece of the grid. What shape is that? And how do we get the area of a rectangle? But those lengths are vectors. And the formula for the area of that vector is the cross product. So I can then take RU and RV and take their cross product. I'm going to do this a lot. What does that give me? If this is RU and this is RV, this cross product sticks out from our surface, which makes that the direction vector for a tangent plane. We did tangent planes. We did fx cross fy, right? Partial derivative of x times the partial derivative of y, and we got the direction of the tangent plane. It's the same equation. We're just not using x and y anymore. We're using u and v. If I pick a point and I look at our cylinder, then I can say, oh, look at, I use a piece of lined notebook paper. The lined notebook paper I have has blue lines going across the page and these red lines on. So there are my circles going in the U direction and my lines going in the V direction. Here's my ruled cylinder. If you roll up your graph paper, it's the same idea, right? Same set of boxes. I can now say, oh, a tangent plane would sit against this surface. I don't actually have to put the little chopsticks through my hat, but I can see that same surface behavior. But if that is the tangent plane, if I took the area of that little rectangle, the area of a parallelogram is the length of this cross product. So I could say, hey, wait a minute. If I take the length of RU cross RV and multiply by DU dV, that would be ds. ds, that would be our surface area behavior. For those of you that play high-resolution video games, when they talk about the polygon count, that's what they're talking about. They're talking about how little the bitty polygons are. I'm making little bitty rectangles. That's my area piece. So if I want the area of my surface, I really want the double integral of this. Notice that's a capital S, not a little s. We use d little s for arc length. I'm using d capital S for surface area. And that becomes this, which, by the way, if our function is a graph, that's the same integral that we did back in chapter 14. Those turn out to be exactly the same thing. Now, I have done something unfortunately tedious by going through the drawings first. There are several very good examples of finding the tangent plane, of computing the surface area, of doing all of these actual calculations on pages 11, 15, 16, 17 examples. I think 8 through 12 are really good versions of these. So I'm not going to do an example here. I want you to read them. The $64,000 question. Why? Why would I do this crazy thing? Well, unfortunately, a lot of the surfaces we deal with in real-world applications are best described parametrically. This surface self-intersects. This is a three-dimensional version of a curve we did in Calc 2, where we found, and we did it for the arc length, that asteroid shape with the curved sides. It was one of our parametric examples. There's that piece of pasta, but not only does it get wound up, it gets smaller as we go up. But what goes on here? That could be used as a real surface. Matter of fact, there are radio telescopes that use this sort of spiral design to better amplify radio waves. That's actually designed as a pickup. A crosscap like this, a self-intersecting surface in 2 dimensions, is used regularly to increase minimization of surface area. I can fold things up that way much better, put them in smaller payloads if I want to deploy a sail or a parachute. How do I get it to be as small as possible? I decide how it's going to compress. I want to be able to do these area calculations so that I can then say, Green's theorem. What was Green's theorem again? Come on, people. What was Green's theorem? I just gave it back to you on the homework I gave you. I got another 5 minutes. Thank you. Green's theorem. That's for when we have an open one. F of B minus F of A, it's the open, the ended one. But when it was closed, if our vector field was conservative, the integral was 0. And if our vector field wasn't conservative, I could either integrate around the edge, or I could integrate across the middle. What if I take that surface, and instead of thinking of that surface as flat in the XY plane, I think of that surface in 3 dimensions? How does Green's theorem work on a surface? Try this one. Because if I can't make Green's theorem work, I'm going to have to invent something brand new to deal with all of these conservative vector fields in 3D, and that's going to be a pain in the ass. I don't want to do that. I'd like to make Green's theorem work, but that means I need to figure out how these work. What's tomorrow? Question and answer. Friday, we're going to start looking at how you integrate on a region defined as a surface in 3D. And then next week, I promise you, I'm putting all of the rules of physics, I'm putting the power of the entire universe in your fingertips. This is the best part of this course. I'm going to teach you how to be gods.